Today, we're going to talk about a fundamental concept in physics called momentum. Previously, we've talked about acceleration, we've talked about mass, we've talked about velocity and position. And momentum is another type of physics quantity that helps us understand rockets. And really, it helps us understand thrust of a rocket and how thrust of a rocket works. So momentum is the velocity of an object times the mass of an object. So if you remember, velocity is a vector. So it has directionality like east, west, north, south, up, down. Mass, on the other hand, does not have directionality. It is a scalar. And when you multiply a vector times a scalar, you get a vector. So momentum is a vector just like velocity or acceleration. It has directionality also. Let's talk for a second about mass. What is mass? Well, we think of mass and weight as being related to each other, and sometimes in our minds we think of them as being the same thing, but they're sort of not the same thing. On Earth, they're sort of interchangeable, but when we talk about mass and weight, what we're really talking about is that weight has to do with the mass times the gravity, all right? Mass, on the other hand, is related to how much stuff is in an object, like how many atoms are in an object and everything. So, for an example, if we take an elephant, Floppy the elephant, let's call the elephant, and we talk about the mass of Floppy the elephant. If we take Floppy the elephant and we move the elephant to different planets in our solar system, Mars, Venus, or the moon, for example, the mass is exactly the same on all of those different bodies. Floppy the elephant's mass, the number of particles and everything, doesn't change from Mars to Venus or the moon. But the elephant's weight changes pretty dramatically on Mars, Venus, or the moon. The elephant weighs significantly less on the moon and Mars because the gravity on Mars and the moon is significantly lower. Venus actually is pretty similar to the Earth, so Floppy the elephant would weigh about the same on Venus as on the Earth. But mass is exactly the same on all of those different bodies. When we take velocity and we multiply that times mass, we get momentum. Velocity is a vector, mass is a scalar. When we multiply those two things together, we get a vector. So momentum is a vector. Remember Newton's laws. We're not going to go into the details of Newton's laws right now, but Newton's laws talked about things like forces, accelerations, masses, right? But really what Newton's laws are talking about is momentum and the change in momentum. So let's look at momentum a little bit more closely. So if we change the momentum of an object, that usually means that we're changing the velocity of the object. So we take something that has like 50 kilograms of mass and it's moving at like 10 meters per second, and we slow that down to like 0 meters per second. That is a change in the momentum, and that usually results by a change in the velocity. And what is a change in velocity? A change in velocity is acceleration. We've been talking a lot about how acceleration is just a change in the velocity. So a change in momentum is the mass times acceleration. Well, what else was mass times acceleration? That was a force. Newton's second law says that force is equal to mass times acceleration. So a change in momentum is a force, just like the mass times acceleration. And so why is that useful? Well, it allows us to do comparisons to things. So let's say that you have a baseball and somebody is throwing a baseball at a very fast speed, and you have a bowling ball and somebody throws a bowling ball at a pretty slow speed. Well, their momentums may be exactly the same because the baseball has very low mass but very fast speed, and a bowling ball has very slow speed but very large mass. So the momentums could be exactly the same. And therefore, the force needed to reduce their momentums to zero could be exactly the same. A fast pitch baseball and a relatively slow moving bowling ball may have exactly the same force to get their momentum to zero. On the other hand, if things are moving at exactly the same speed, but they have very different masses, they have very different momentums. So a car moving at 100 kilometers an hour and a truck moving at 100 kilometers an hour, they're going exactly the same speed, but their momentums are very different from each other. And that has a big impact on how we think about cars and trucks. So if a car going 100 miles an hour hits a brick wall, it has a very different impact on that brick wall than if a truck hits a brick wall going 100 kilometers an hour. They have very different momentums, and therefore the forces they impart will be very different from each other. So the other side of a force, what we've been talking about so far, is that the force is equal to the mass times acceleration, which is a change in velocity. But interestingly, if we generalize this a little bit, we can actually say that the force is also equal to a change in mass times the velocity. Okay? So that has some ramifications on how we think of thrust when we think of rockets. So let's go back to our cannon on a boat example. So the change in the boat's momentum is equal to the mass of the cannonball times the velocity of the cannonball, because the boat is losing the mass of the cannonball. That mass of the cannonball is going off in one direction with a given velocity. So the change in the boat's momentum is that change in the mass, which is the cannonball's mass, times the velocity of the cannonball. Okay? There's an action and a reaction like in Newton's third law. The change in the boat's momentum is the change in the cannonball's momentum also. So what does this have to do with rockets? Well, let's say we take a cannon and we orient the cannon so it's pointed straight down. And we start shooting cannonballs very rapidly. What will happen? Well, that cannon will start going up. Just like the boat started moving in one direction while the cannonball moved in the other direction, if you take a cannon and you aim it down and you shoot cannonballs down, the balls will move down, the cannon will move up. So what does this have to do with rockets? Well, a cannon pointed straight down shooting cannonballs is exactly the same as a rocket that's pointed up and it is thrusting down. The stuff coming out of the back of the rocket is not just pretty lights and stuff. It's actually stuff. It's molecules and atoms and stuff coming out of the back, and it's moving very, very, very rapidly. So each little particle that's coming out of the back of the rocket has some momentum to it, and it is imparting that momentum to the rocket. That rocket is losing that mass at some velocity, and therefore it's being pushed up. A force is being applied to the rocket, and that is thrust. Thrust is just all of the stuff coming out of the back of the rocket at a certain velocity. And that's how we can think of thrust of a rocket. So in summary, momentum, small things moving fast can have the same momentum as big things moving slow. For example, the thrust of a rocket is a bunch of little itty bitty particles that are moving very, very, very fast. And the rocket's momentum is exactly the same as all of those little particles. One big thing moving slow is the same as all of these little things moving very, very fast. The change in the momentum involves either changes in velocity or changes in mass, and you can do both, and that gives you a force.